Hello everyone. Today we will talk about the hardware of the MC1322X. This is part 1 of this presentation. We will talk about the design architecture of this chip and what are the different types of memories within it, such as the RAM, ROM, and the flash. Of course, we will also talk about the GPIO, the UART, and the timer modules as well. Before we dig into this chip in particular, let me start with defining what a microcontroller is. A microcontroller, sometimes known as the MCU, is a small computer on a single integrated circuit containing a processor core, memory, and programmable input-output peripherals. Program memory is in the form of a NOR flash or an OTP-ROM, is also included on the chip, as well as a typically small amount of RAM. Microcontrollers are designed for embedded applications, in contrast to the microprocessors used in personal computers or other general support applications. Microcontrollers are used in automatically controlled products and devices such as automobile engine control systems, implanted medical devices, remote controls, office machines, appliances, power tools, toys, and many other embedded systems. By reducing the size and cost compared to a design that uses a separate microprocessor, memory, and input-output devices, microcontrollers make it economically to digitally control even more devices and processes. Mixed-signal microcontrollers are common, integrating analog components needed to control non-digital electronic systems. Now let's see some history about microprocessors. The first one was introduced in 1971. It was called the 4-bit Intel 4004. Later on, Intel introduced the 8008 and other more capable microprocessors becoming available over the next several years. However, both processors, the 4004 and the 8008, they required external chips to implement a working system, raising the total system cost and making it impossible to economically computerize appliances. Fast forward to 1993, the introduction of something called the EEPROM memory allowed microcontrollers to be electrically erased quickly without an expensive package as required by the regular EPROMs, allowing both rapid prototyping and in-system programming. The same year, Amtel introduced the first microcontroller using flash memory, a special type of EEPROM. Other companies rapidly followed suit with both memory types. The cost has plummeted over the years, and over time, with the cheapest 8-bit microcontrollers being available for under 25 cents in quantity in 2009, and some 32-bit microcontrollers were sold for about $1 for similar quantities. Nowadays, microcontrollers are cheap and readily available for hobbyists with large open communities around certain processors, such as the one we will feature in this presentation. In the future, MRAM could potentially be used in microcontrollers as it has infinite endurance and its incremental semiconductor wafer process cost is relatively low. A typical home in a developed country is usually or is likely to have only 4 general-purpose microprocessors, such as those used in laptops and computers, but around 3 dozen microcontrollers, such as those found in their refrigerators or any other home appliances. A typical mid-range automobile has as many as 30 or more microcontrollers. They can also be found in many electrical devices such as washing machines, microwave ovens, and telephones. Microcontrollers usually contain from several to dozens of general-purpose input-output pins that are known as the GPIO, and we will go in detail into this particular module in a bit. But first, let me tell you that GPIO pins are software configurable to either an input or output state. When GPIO pins are configured to an input state, they are often used to read sensors or external signals. Configured to the output state, GPIO pins can drive external devices such as LED lights or motors or whatnot. Many embedded microprocessors include a variety of timers as well, and timer is an important module that we will talk about in a bit as well. One of the most common types of timers is the programmable interval timer known as the PIT. A PIT may either count down from some value to 0 or count up to the capacity of the count register, overflowing to 0. Once it reaches 0, it sends an interrupt to the processor indicating that it has finished counting. This is how the timer works in general. This is useful for devices such as thermostats, which periodically test the temperature around them to see if they need to turn the air conditioner on or the heater on. A dedicated pulse width modulation known as the PWM is also another important section of the chip, but it will not be talked about in detail in this presentation. It's generally a block that makes it possible for the CPU to control power converters, resistive loads, motors, etc. without using lots of CPU resources in tight timer loops. And then we will talk about the universal asynchronous receiver and transmitter, known as the UART block, which makes it possible to receive and transmit data over a serial line with very little load on the CPU. Dedicated on-chip hardware also often includes capabilities to communicate with other devices or other chips in digital formats, such as the serial peripheral interface known as the SPI. Now that we talked about the architecture of such microcontrollers, let me introduce you to Zigbee. Zigbee is a wireless standard when we talk about the Internet of Things. It's a point-to-point command protocol that is easy to use, has good range, and is very reliable. Most specifications in particular, out of which the most popular is the 100 milliwatt module with external antenna. This is one of the best specifications that one can use, and it's reliable and has excellent range with high power signal. So if you want to install a certain Internet of Things device that is within a building, for example, it is important that you use an external antenna to make sure that the receiving and the transmission of the signal is in good condition. Now, the announcement of the chip that we're talking about, that is the MC1322X, was done in Texas in March of 2007 by the company Freescale. Freescale Semiconductor has introduced a single chip platform solution based on the Zigbee specification we just talked about. It is designed to deliver the industry's lowest power consumption and highest performance. The MC1322X platform is engineered to support battery life of up to 20 years, doubling the expectations for current Zigbee solutions. Here is how the chip is being used in a USB device, and what is particular about this device is the fact that it uses low power. So the MC1322X is inherently a very low power device, but it also has extensive power management and an onboard buck regulator option to maximize battery life. Another great feature is the high density, low component count, and finally, its use of a 32-bit ARM7 processor. That makes it really powerful. And now, let me show you a high-level overview of this particular chip, the MC1322X. We will be talking in particular in this presentation about the memory and the types of memories, obviously the ROM, the SRAM, the static RAM, and also the flash module. And we will be talking about the GPIO and in particular it's located in this portion of the diagram, and we'll talk about the UART, which is located right here. There are two of them, and the timer is located right here. So let me start by talking about the memory. The memory, as we talked about earlier, it consists of the RAM, the SRAM in particular, the ROM, and the serial flash. All the read or write accesses require a minimum of 2 system clock cycles. Talking about the RAM to begin with, the RAMs have been divided to allow for power savings. So while sleeping, the above RAM blocks can be turned on and or off. And in particular, as we talked about, there is RAM 0, RAM 1, 2, and 3. RAM 0 is 8 kilobytes, and RAM 1 is 24, while RAM 2 and RAM 3 are 32 kilobytes each. A read or write access requires a minimum of 2 system clocks, as we talked about, and depending on the amount of RAM power during the sleep, the boot time may be longer with less RAM, as the non-powered RAM must be reloaded from flash. While sleeping, the above RAM blocks can be turned off, and the RAM remainder can be placed in a low voltage mode for data retention. Moving on to talk about the ROM. The ROM size is about 80 kilowords, and initially it contains the bootstrap code or the drivers that are needed to reset the device if need be, and it also is all the code that is needed to start off the communication within the chip to the external world. Now, finally, we talk about the serial flash, which is the memory needed to save data, save your program or whatnot onto this device. It's a 128 kilobyte serial flash memory that can be mirrored into the 96 kilobyte RAM, and the serial flash is accessed via an internal dedicated SPI module. The flash is accessed at boot time to load or initialize the RAM. All the actual CPU program and the data access is from the RAM or the ROM. And now let me talk about the advantages of using the serial flash. This is something that we have done as an external research on the side to add to the value of this presentation. The advantages of having a serial flash instead of parallel is, first, it reduces the reduced board space. Since serial flash transmits and receives data 1 bit at a time sequentially, serial flash requires fewer wires on the printed circuit board, what is known as the PCB, and thus less board space. Second, there is lower power consumption. Considering that power is directly proportional to the current, with the low maximum standby current of about 5 microamps, then the serial flash consumes much less power than parallel flash. And finally, the low costs, the direct result of smaller board space and obviously a simpler printed circuit board. Let's start with the GPIO, which is the general purpose input-output. It's the primary control over the input and output ports of the microcontroller, which enables it to communicate with external signals. The GPIO pins have shared functionality with other modules, as we will see next. When they are not used by other peripheral modules, the I/O ports are configurable as input or output. Now, each of the 64 ports that we will see has dataset and control register bits that determine their operation. The GPIO module, however, reserves 4 registers for function, select, control, since it has 4 modes to select from. Function 0 is the default mode, and then you have also among the alternate modes is function 1, which is the peripheral controlled mode. If the peripherals are enabled, meaning that this is the function that sets the port to work with another peripheral module, such as the timer or the UART. The GPIO pin enables the peripheral to read data on the I/O pad, and when put into the GPIO mode, the port I/O control functions as the GPIO pad direction control, GPIO data control, peripheral port control, also the pin mapping within the GPIO control registers. Another GPIO functions that are controlled independently from the function select are the pull up and the pull down, the hysteresis, and the pad keeper functions. The parallel I/O features include a total of 64 general purpose I/O pins, individual control for each pin when in the GPIO mode, a pad hysteresis enables, and also software controlled pull up and pull downs on each pin, and when not in use, the GPIO, the I/O provided alternative functions. 8 kBi pins are kept alive during hibernate or doze, 4 kBi are output and 4 are input. The input can be used as wake-up interrupts. In regards to the UART, which is the Universal Asynchronous Receiver and Transmitter module, it is used to communicate with external controllers. The UART module consists of two independent modules, the UART1 and the 2, as we have seen earlier in the diagram. Access to the UART is through its data and control registers, and data transmission and reception are in the 8-bit length. The UART provides hardware support for the RTS input and the CTS output. The RTS is what is known as the ready-to-send input, and the CTS is the clear-to-send output. And also the UART recognizes interrupts caused by receiver and transmitter. The UART module is programmed through memory mapped registers. Control register is used to specify transmission parameters, while status register is used to specify interrupt, request status, and identity errors. There's also the data register, a buffer control register, a level control register, and a baud rate divider register. Moving on to the timer module its main purpose is to count internal or external events and to compare the values with the preset values. The external inputs of each counter or timer are shareable and can be counted and used as counter or as a timer commands. The timer module has 4 external timer input or output, which are known as the TIO pins. And finally, the counter timer is programmable and has several functional modes. In addition, the timer module recognizes a few types of interrupts, specifically timer compare interrupts, which is generated when a match occurs, timer overflow interrupts, which is generated when a counter rolls over to its maximum value. We mentioned this earlier, it resets back to 0. And a timer input edge interrupts, which is generated when there is a transition of the input signal. The timer has a number of registers with different functions as well. Specifically, a compare register, a capture, a load, a hold, a counter, a control, and also a channel enable register. And finally, our thoughts to this particular chip, to the MC1322X. I was looking around and we all kind of discussed that the market is humongous. There are so many options out there that can make use of this particular chip, especially when it comes to security, to patient monitoring systems, to TV, media controllers, even in the irrigation and the agriculture industry, and even in security inside of your house applications. There is so much out there that can make use of this chip. And in fact, we were able to find online a special kit that you can see the picture of here. It's a startup kit that you can use to build applications within the Internet of Things. And the future will hold a lot of things because there is a lot to be done in terms of usage for this particular chip, and also it's nice to see how this chip is going to be reduced in size as years go by. And keep in mind that this is not the only chip. There are others out there that can do the same thing or probably more. So there will be competition among these manufacturers to provide a platform and probably smaller chips that can do even more things than what is currently being done right now. We conclude this presentation with a list of our references. Hope you enjoyed it, and until next time, have a good day.